Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss our upcoming videos, subscribe to the channel and turn on the notification bell to receive all updates. As we know, the universe is expanding, and there are two main possibilities for its fate. The expansion could continue indefinitely, or it could stop and eventually contract. But which of these hypotheses is correct? In 1929, astronomer Edwin Hubble made a discovery that would forever change our understanding of the universe. Galaxies were moving away from each other, and the speed at which they recede is directly proportional to their distance. This discovery led to the formulation of Hubble's law, one of the cornerstones of modern cosmology, suggesting that the universe is expanding. Until then, it was believed that the universe was static, as even Einstein had initially postulated in his version of general relativity. The idea of an expanding universe immediately altered cosmological theories and raised new questions about its fate. One of the main theories guiding our understanding of the universe's evolution is based on Friedmann's equation, which describes the expansion of a homogeneous and isotropic universe, like ours. According to this theory, the fate of the universe depends on the amount of matter, both visible and dark, and energy, including dark energy, present. In particular, there are three main scenarios that depend on the value of a cosmological quantity called the density parameter, omega, which compares the density of matter and energy in the universe to the critical density needed to maintain a stable universe. 1. Open universe. Omega less than 1, expansion continues indefinitely, and the universe becomes increasingly cold and empty over time, with a slow extinction of stars. 2. Closed universe. Omega greater than 1, expansion stops, and the universe begins to contract, potentially ending in a big crunch, where all matter and energy collapse back into a single point. 3. Flat universe. Omega equals 1, expansion gradually slows down but never completely stops, tending to halt only after an infinite amount of time. Until the 1990s, scientists believed the universe was likely closed or flat. However, new observations disrupted this view. In 1998, astronomy made a shocking discovery. Not only was the universe's expansion continuing, but it was accelerating. This phenomenon was attributed to a mysterious force called dark energy, a type of energy that permeates space and has a repulsive effect, opposite to gravity. The discovery came from studies on type Ia supernovae, which are stellar explosions used as standard candles to measure cosmic distances. Observations showed that the most distant supernovae were dimmer than expected, indicating that expansion was accelerating. Dark energy accounts for about 68% of the universe's total energy, while dark matter, which makes up about 27%, and visible matter, which represents only 5%, form the remaining components. This led scientists to radically rethink their ideas about the universe's fate. If dark energy continues to accelerate expansion, the universe could expand indefinitely, with galaxies moving farther and farther apart. The most accepted theory incorporating dark energy is the standard cosmological model, based on Einstein's general relativity. However, the concept of dark energy was initially introduced by Einstein in 1917 as a cosmological constant, lambda, a term he added to his equations to maintain a static universe, in line with the prevailing ideas of the time. After the discovery of the universe's expansion, Einstein abandoned the cosmological constant, calling it his greatest blunder. However, the discovery of accelerated expansion revived the idea that dark energy might be described precisely as a cosmological constant, although some scientists propose more complex models. The Dark Energy Spectroscopic Instrument, DESI, is a cutting-edge experiment aiming to create a detailed 3D map of the universe by studying over 35 million galaxies. DESI is using a broad spectrum of light to measure the evolution of large-scale structures, helping to better understand dark energy. Scientists are trying to determine whether dark energy is truly a cosmological constant or if it could vary over time, influencing the expansion rate differently. One emerging curiosity from Dacey is that there may be a correlation between the distribution of matter and the acceleration of expansion. Early analyses suggest that dark energy might not be constant but rather a dynamic force that changes over time, potentially impacting the universe's final fate. If these observations prove correct, the universe could go through phases of accelerated expansion followed by periods of slowdown and possibly even a final contraction. Beyond Einstein's cosmological constant, other theories suggest that the universe might evolve in even more complex ways. Some scientists are exploring the concept of quintessence, a form of dark energy that changes over time. Unlike the cosmological constant, which remains unchanged, quintessence is a substance that evolves and might be responsible for the accelerating expansion. Quintessence would have an energy density that decreases over time but could reverse its influence in the future, leading to contraction. Another fascinating theory is the Big Rip model. In this scenario, dark energy could intensify to the point where, eventually, repulsion becomes so strong that it distorts and destroys galaxies, stars, and even atoms, leading to a cataclysmic end of the universe. Cosmological curiosities. 1. The age of the universe. According to the latest measurements, the universe is about 13.8 billion years old, a figure confirmed by the Planck mission, which studied the cosmic microwave background radiation. 2. Mysterious dark matter. Although dark matter does not emit light, it is believed to make up about 27% of the universe's mass. 2. Scientists still do not know its composition, but it is hypothesized to be made of particles like WIMPs, weakly interacting massive particles. 3. The effect of gravity. While dark energy accelerates expansion, gravity still dominates on smaller scales, keeping galaxies and star systems together. 4. The observable horizon. The observable universe has a radius of about 46 billion light-years, but we cannot see beyond this limit due to the finite speed of light. The fate of the universe remains one of science's great unanswered questions. Our knowledge has advanced tremendously, but with every new discovery, more questions arise. The combination of advanced experiments like Dacey, continued supernova observations, and research on dark matter and dark energy might provide the answers we seek. But one thing is certain. The fate of the universe could be far more surprising and complex than we ever imagined. Thank you for joining us on this journey. Leave a like and subscribe so you don't miss the next videos.